It's competition and code reports.
Mm-hmm.
Code report and competition.
Yeah, I think
Right,
it's
yeah.
It's different. Okay,
Okay.
we're recording, right? Yeah, I see the stop the clock going.
We're doing it live.
Alrighty then. So this is code report and competition. And yeah, I guess I put this together and we'll see what I did. I can't click on this slide, I have to do this. Alright, so first section will be why do we need code reports? And so and I think at the time we put this together, this was the most recent adopted version of the IBC. But the 2015 International Building Code, or IBC, basically allows materials that are not included in the design code. So FRP and FRCM would be two materials not included in that code. The document basically allows building officials, people that work for the government that help to review and approve different projects. They can accept materials as long as they have a code report, and those materials can be used in the area they're responsible for in the United States. So 2014 ACI 318 version. There actually may be a more recent version now, but I don't believe that's been adopted yet. Maybe it has.
There's a 2019 version that just came out.
Okay, so that's not adopted yet. So it usually takes about a year for codes to be adopted into use. And so this, you guys know ACI 318, I think most of you do that. We use this for some of our design templates, but it's the building code requirements for structural concrete. So acceptance criterias are what the ICC ES, so International Code Council Evaluation Service, are the ones in charge of acceptance criterias, and AC is short for acceptance criteria, and AC 125 is the document that we had to perform our FRP testing in order to obtain a code report. So our FRP code report is ESR, or Evaluation Service Report number 3403. So that was what we used to get our code report, and I think I've got more detail on our testing later, maybe? I don't know if I did or not.
Yeah.
So this is a slide I grabbed from another presentation, but our FRCM code report is ESR 3506, and that's a fairly new code report for us. And that's our FRCM products, fabric reinforced cementitious matrix. That's sort of a mouthful. And that has all of our FRCM grids, so CSS UCG, BCG, and HBCG. And this has certain structural applications included in it, not very many seismic applications. But this is the same list of structural applications we originally had in our FRP code report until we just added all of our seismic to that. So I guess I have some other slides that go through more details.
And
Yes.
just one thing about, I think we talked about the different criterias before, but this is AC 125 for FRP. And for FRCM, there's a different acceptance criteria called AC 434, and that's what this code report is tested to.
Right. Yeah, thank you. So here's some pictures of the column axial strengthening that we did. So this was done at Griff's old lab, North Carolina State. Yeah. Wolfpack?
Yeah.
Yeah.
Wolfpack.
It's crazy. So this particular test rig basically put a column in between plates and squished it. So try to axially compress the column. And so you'll see this round column has a crack here that was caused by the concrete expanding, and we had grid around in a hoop trying to confine that column together. You see similar cracks here on the rectangular version. Um, and yeah, so we did a handful of specimens there, which this is not very big, um, but yeah, this gave, I think I created this slide for S&P just so they can see what percentage of strength increase we were able to get with FRCM strengthening. So anywhere from 18% to almost 100% increase in strength. So now we can't use all of that strength in our design. We have to use all of the phi factors and the knockdown factors, but this will give you an idea of how much stronger elements can be with our materials. Um, Let me know if you want to pause and do like a knowledge check with the team or not, if I'm going too fast. So, all right. Right, since Hugh's not here, it's up to you guys. So let's see. So that first table was round columns. This is rectangular columns. So again, we're a little bit different strength for this, as you probably can tell. So you'll see how the strength increases are much different than the round. So round is a much stronger section. Rectangular is not. So we did the long face of the column. Definitely doesn't work as well. So you get lower strength increases. And actually had one that was less strong. So.
But looking at it looks like the 4-ply on the bottom and the 1-ply are like the same.
Yep. So not really, doesn't really make sense to add 4 plies on a rectangular column. Well, doesn't necessarily make sense for ultimate, but take all the knockdown factors out, that might actually pay off.
Yeah.
Yeah.
Yeah, so you resist higher load. But that is interesting to see the data.
Yeah.
That a circular section is much better than a
Right.
rectangular section.
So beam flexural strengthening, we actually did this testing at our lab in Stockton, at Ty Guild Lab. So we had to rent this big, huge tent, lay all the beams out, and then we had a contractor come in and sandblast all the beams. And then we did the FRCM strengthening inside the tent to help confine all the dust and everything from blowing everywhere. So, and then afterwards we set up sprinklers to wet cure, and we laid burlap over all the beams.
It's like something at least in Ho Chi Minh City, you don't have
Well, that's true, they don't need it.
a lawn.
Right.
Like if you have grass that you need to water, I guess in the rainy season you wouldn't ever need to do that. But like in California, if you have a house with grass around it, or the grass your lawn or your yard, and you need to water the grass, you put a device out that sprays water all over it. This is like watering plants, but watering it's meant to water a big area.
Oh, I don't even have it up on the screen.
Okay.
Like that one.
Yeah.
Sprays water. So we had it going on a timer, spraying water over all the beams to keep them wet while they cured. Wet cure, which is why we say wet cure on our data sheet and specs.
But so you said for the surface preparation, a lot of people use a grinder, a mechanical grinder. I think we showed you pictures of those before we grind the concrete surface before applying the FRP. But that's a lot of manual labor. It's very hard work to hold the grinder and grind against the concrete. And so it looks like for this, instead of having the lab guys grind a bunch, they got someone to sandblast, which is it's a big gun that shoots out sand at a very high speed and does this basically the same thing as grinding, but with much less work.
Well, remember this is FRCM too, right? So we need a CSP 6 to 9, so very rough. You can't get that with a grinder.
Oh, right.
To get that with a grinder, you have to like gouge, and that's not the way to do it. So pretty much for FRCM, you have to grinder or walk behind scabbler or something that makes a really rough surface. So grinding would not work on this. So
Oh, yeah, yeah.
yeah.
Good point.
So the image on the right shows, I think that was one of our flexural beam specimens, and this is a picture looking at the bottom side where the grid basically slipped in the crack, and that was the failure of that particular beam. Yeah, you see the grid inside. Well, let me get the pointer back. You see the grid pieces about every inch or so.
But so the grid did not rupture,
Correct.
right? So the carbon is still.
We probably, if we kept pushing, it would have ruptured eventually, or something would have given, but we just stopped because we weren't going to get any more load. So.
But so the slip is like when the grid, like basically breaks out of one of the like concrete pieces
Yes.
connecting it.
Correct. Yep. So this is our flexural strengthening. So we just had FRCM on the bottom of the same beams we did for FRP. And so this is again the strength increase for each specimen ranging from 15% to 122%, depending on the specimen type. So very good strength increases there. And then we also did beam shear strengthening. You see these areas are strain gauges to measure the strain, and we had U-wraps of FRCM at those strain gauges. And then you see again the grid slip at the shear crack. So the vertical UCG grid there.
Oh, there's more beam shear.
Yeah, one more.
Oh.
So the beam shear results, strength increases from at least 35% looks like, up to 94%. So pretty good strength increases there. So one thing to mention here is we, in the design calculations, we are not able to use the extra concrete thickness we're adding. And when we do 4 layers of grid, it's quite a bit, quite a thick extra concrete portion. So the strengths you see here, the ultimate strengths were much higher than we, right? It's pretty big beam by the time you're adding 4 layers. So that's one of the reasons why we get such a large strength increase from using 4 layers. But we can't take advantage of that in our calculations. Our calculation would show it's much lower than that. But the beam was only 8 inches wide by 12 inches deep, and when you add 4 layers, it becomes like a probably 12-inch wide or 13-inch wide beam. You wanted to challenge yourself and not use the mouse?
I feel like it's easier to draw without the mouse.
Oh.
So you can add the strength from the grid, the VF, from the FRCM, but all of this extra concrete should add to the VC, the shear capacity of the concrete, but the design guide says we're not allowed to use that extra strength. So it's very conservative in that way.
So I'm actually a voting member. I sit on the committee that writes the guidelines, ACI 549. So if we show enough data, we might actually be able to change the design equations and get more strength out of FRCM by adding concrete. Like if you make sure you do the adhesion check that you have good adhesion from the FRCM mortar to the substrate, then maybe we can get a higher strength one day. Was there something else you wanted to say about beam shear?
Just want to break for a second.
Pause for a second.
Yeah.
talk amongst yourselves.
Yeah, take a minute and let us know if you have any questions. You can look over what we've covered so far and see if there's anything. I think I remember trying to draw a picture of grids like that. I think it worked very well.
Mm. In the past presentation, well, like FRCM or something.
Yeah, when we were covering FRC. Yeah.
Hỏi nghe này.
I thought I heard somebody say Griff. Maybe not.
Don't nghe được.
Super clear, apparently. They're okay? Super clear?
They didn't ask anything.
Alright.
Yes.
When we transcend the beam with the high train coverage, when we read the number of layers of MICM, the percent of the grid is the same with one layer and four layer.
So we always used, so those designations, L600 is S&P Clever's skew for the UCG grid. So we always use UCG, so it's either one layer of UCG or 4 layers of UCG.
But the same percent agrees for the high train coverage.
Right,
Yeah.
yeah. And that probably will tell you that the grid isn't doing much,
Yeah.
but the VC that we're not allowed to use from the FRCM is giving us a lot of strength maybe. So
But
yeah,
that is weird that you don't have any strength increase from the next 3 layers.
yeah,
I mean, not even from the VC.
right. Oh, I see what he's saying, yeah.
It's the same, like all of these values are about the same.
Yep.
Whether it's 1 layer of grid or 4 layers of grid. That seems strange.
It does.
I don't know why.
I don't know why either.
But then up here for the lower strength
Yeah, there's
concrete,
a clear difference.
yeah, it's much different.
Well, maybe the base concrete is so strong that it's very minor to add, because the grid isn't that much, right? There's 1 inch gap between the grid, so you're not really adding very much fiber to a beam that's already that strong. So maybe, and that is odd too, that it's about the same, like the 418 kilonewton range is about the same as the 4 layers of the low strength concrete. So I don't know. Yeah. Things that make you go, Okay. So we also did CMU wall out of plane strengthening. So taking a wall and pushing it and pulling it in and out of plane. And this shows, you can see, it's not the biggest picture, well, it's better up there, but you can see how the crack started in the FRCM, went through the bond line and went right into the masonry. So this acted like a monolithic unit, like it was all one piece, not a CMU wall with FRCM on each side. So we showed really good bond with our FRCM to masonry, so that was good to see. And strength increases from only 9% to over 100%. I think we probably had an issue with the test setup here. It probably failed somewhere else, so we might be able to throw out that result. But
Yeah, I think it might have had to do with the anchorage on the bottom. There was like some kind of failure there, and that's why it failed so early. So more of a test
setup issue,
Yeah, a test setup problem than a problem with the wall or the FRCM.
We also did CMU wall in plane shear strengthening. Now this was unreinforced and ungrouted CMU, so no rebar, no grout. This you can see very small crack, diagonal crack here on the back side, so we only strengthened on one side of the wall, and this is the stair step crack that happens on the front of the wall. I can't remember if this is a control unstrengthened specimen or a strengthened specimen, but and then we have strain gauges here. And those strengths, actually, we didn't have a control specimen for the large portion of these tests. Actually, I think that's in the wrong spot, but that's fine. But we were able to get pretty significant strength gains, almost 200% on some of these.
From the calculated value?
Yeah, from the control value. We did one control, I think for the high strength, the high strength block, we were able to do a control. So those are just comparing the control
Oh, so the
values to
low strength, okay.
the ultimate, yeah. The low strength just failed. That was a tricky setup that we messed up the first one, so. And so our competitors that have FRCM code reports right now are two different companies. Ruridel is one of them. And they have a similar system to our FRCM system with a mortar and a grid. They have to hand trowel their mortar, so they can't shotcrete it. Yep, so they got to mix it in a bucket and then throw it up on the wall and move it around with a trowel, where we can shotcrete ours. Caracol is another competitor, and they have a steel reinforced grout system. So they have like a welded wire fabric, but a steel grid that they embed in their mortar, and so theirs has a potential to corrode in the future like rebar does. So we don't see too many projects with their system on it, or we don't hear that they compete with us very often. So yes?
Is Caracol like a flexible steel, like it's like a chicken wire kind of thing?
Yeah, it's very light, yeah. And then that was a question to S&P. We don't need to talk about the last bullet. So our recent updates to our FRP code report, we added seismic strengthening. I think this was last year, I think. So we did ductility, added ductility for column strengthening, ductility for beam strengthening. We added in-plane shear strengthening of slabs and in-plane shear strengthening of concrete walls. And on the concrete walls, actually Aniket is on his way to Colombia next week to watch the tests of our FRP. I think I have pictures of them. We'll go back. But so these are the wall specimens with no anchors, but we're gonna do wall specimens with FRP anchors and see if we get better results and see if we get high strains, so we can adjust our design procedures. So Aniket's gonna go, this is in the country of Colombia in South America, and Aniket's gonna go watch the testing because he's got all this free time.
It's good for Berkeley.
It's good for what?
Berkeley High School.
Oh
We
yes,
did yesterday.
right. That's
Yeah.
right. Berkeley, yeah.
So one thing, or do you have one?
No, I was trying to think of what else I wanted to say about that, but if you have something, please.
Yeah, so the way the code report works is different from how you normally design a structure. So if you use ACI 318 to design a reinforced concrete structure, you have to use the strength of the concrete and the strength of the rebar and use all the design equations to find the strength of the building, of the member. And so you rely on the equations to calculate the strength. And even if you haven't done a test on a certain kind of beam, you can still design that kind of beam. The code report is a little bit different, where they specifically say that you can only use FRP on a certain kind of member for a certain kind of loading. So the way design usually works is you take your materials, your concrete and your steel, and you can design it in any way you want to. But with a code report, they limit what you can design your FRP for. Even though we have equations in ACI 440 for all different types of applications, the code report says, for instance, if you want to do in-plane shear strengthening of a slab, then you're not allowed to apply that on a job in the real world unless you have testing on that in your code report. There isn't really any rule anywhere telling people that they have to read the code report and look for the certain application to make sure that you can apply. In the past, that has never been a problem. But a few years ago, I think it was Fife. Fife has, I think, the code report with the most different types of applications, and they got somebody in Southern California near Los Angeles to write a book stating that you can't use FRP for any strengthening type that is not in your code report. So at that point, some engineers didn't want to use our materials in Southern California because we didn't have these in our code report. So the big impetus, the cause for this testing was because we couldn't win these jobs in Southern California without having these items in our code report. So that was kind of the main reason why we added them. And it's a weird rule that you have to have a test to do a kind of strengthening, because that's not, if you know how strong the FRP is in tension and you have the design equations, you shouldn't have to test everything. But people are
Fife.
Yeah. Our competitors are fighting to try to keep us from winning jobs, so
they can win them.
yeah, so we have to play the game to win these jobs.
Thank you. So here's some pictures of our column ductility strengthening. The one on the left is unstrengthened, so no FRP. And then we had also glass specimens and carbon specimens. So you can see we basically loaded the top of the column and moved it back and forth until the column broke.
Where was this testing done?
This testing was done at NC State.
Woo!
You knew the answer to that because you saw the red, and you probably already know that. But anyway, so weird, so creepy. Do you have something else to add?
Yeah, well, I think about this testing, column ductility strengthening. So for column ductility, what are we strengthening? Like, what strengthening type is this? Is this like a shear?
This would be like flexural. We also did shear.
It's so is it like flexural and bending? Or sorry, like axial, combined axial and bending?
I'm not sure if they added axial load on these specimens or not, but they racked them back and forth. So it's basically confining for it. Well, they have gaps though. I was going to say confining for a higher F prime C, and then you inherently get flexural strength out of that.
Mm-hmm.
Basically what we had to show, and I think we had to show, oh, that's column flexural strengthening. Now I'm confusing myself. But we had to show increased levels of ductility. So basically the column has to be able to extend. I'm not sure how to explain ductility.
Draw a picture.
Well, I was hoping that this would do that, but
You have to increase the displacement, right?
right.
So instead of
So with each
increasing,
cycle, yeah, you have to get a more bigger and bigger displacement, yeah.
yeah, so instead of increasing the strength capacity in load in like kips, you're increasing the displacement capacity in inches. So it's able to move more before it fails.
Before it fails, right.
And I think that the reason for the column ductility, even though there are gaps in between, I think you are confining that concrete.
Right, so I think if our column shear test and our column flexural test show increased levels of ductility, then we get the word ductility added in our code report. There's not a specific ductility test we had to do. And so I think actually these are the shear strengthening specimens I included in the picture. And then I didn't actually show a flexural one, but the flexural ones were basically just, I think we did either a 12-inch or 24-inch wide strip just at the bottom of the column only, and that was it, just in the place it would fail.
So that was like axial and bending then, right?
I have to look back at the test report to
see
see
if
if
it
we
was axial.
axially loaded it or not.
But so I think for these specimens, this is the control specimen, and they purposefully designed it with very few stirrups. The stirrups were very far apart, and so that when they loaded the column, instead of failing in flexure, it failed in shear because it was very weak in shear. And then they added the FRP to increase the shear capacity.
We maybe confused more than we helped on that discussion, but so for column shear strengthening, we got 15 to 24% increases, depending on the fabric, what type of fabric, and the concrete strength. We tested only one layer, so carbon, it looks like we only did one layer of 11 ounce, and we did 1 or 2 layers of glass fabric. Column flexural strengthening, this is the chart I included in the presentation to show basically the increased levels of ductility, and this was from our test report that went to ICCES to review and approve.
And so,
sorry.
Well, on that graph, the blue specimen, is that the control?
Yes.
So this is, I think the word for this is a hysteresis.
Yes, loops.
But it's a graph where the x-axis is the displacement in inches, and the y-axis is the load in pounds. And so the blue specimen had no FRP on it, and so it's loaded in both directions. So there's a positive and negative load, and positive and negative displacement. And so the column is standing up straight, and it's pushed and pulled back and forth, and the amount that it's pushed and pulled is controlled in the experiment. So you can see there's even spacing between each cycle of loading. And so the blue specimen had no FRP. And so you can see that after it deformed, maybe 3 inches? Right here is about 3 inches. That was when it failed. But the specimens that had FRP, the one with carbon FRP looks like it made it about 7 inches. And the one with glass FRP looks like it made it about 9 inches. So by adding the FRP, you're able to increase the ductility, the distance of deformation, by a factor of about 2 times or up to 3 times.
Good summary. So we did beam ductility testing, but we didn't actually get results that showed increased level of ductility. I was a little disappointed in the lab because they just had strengthened it with FRP on the bottom and no wraps at the end to keep it confined or keep it adhered. And so we're actually retesting that next week, I think, in Miami. I don't believe Aniket's going to be able to attend that test, even though he wanted to. So that's being redone right now. And once that testing's done, and we do have the ability to add ductility to our FRP code report, then our language in the code report will change slightly as a result of that successful test. So
So for the beam ductility strengthening, do they like, is it just in one direction,
Yes,
but they do like increasing displacement?
I believe so, yes.
So what difference between this and fatigue? Fatigue. Like to make a fatigue.
Ah, right, it's fatigue loading, yeah. That's the intent. It's like to act like a moment frame beam or whatever.
But fatigue loading is the same load.
Oh,
It's not
yeah,
cyclic.
Oh, so this one you increase every loop.
Yeah. So for ductility, you're looking at how does it respond to increasing.
so
Yes,
they're testing to figure 3, so it increases the load. Figure 3 in AC 125.
Yeah. We can pull that up.
So we are not retesting that exact beam. We're going to actually learn a lesson from our first test and actually add complete fully wrapped hoops at the ends of the flexural strip to help keep it confined. So excuse me. So tired from digesting that burger last night. It's like one of the last pages.
So this is AC 125 that tells you how you have to test things for seismic. And so this is the graph that they give you. And so this is mu, the Greek letter mu, and in this case it stands for the ductility factor. And I believe that mu equals 1 is where they define yielding, first yield. So it's like as you're testing something, a reinforced concrete member, it'll increase in load in a linear way, a straight line. The load and displacement increase the same, and then at some point that changes. Like if you're looking at displacement and load, and whenever it starts to soften, it's not linear anymore. When it starts to yield, then you define that as your yield point. So when you run this test in the laboratory, you have a computer readout that compares the displacement with the load. And you can see on the computer the test is going on there. You can see the wall, but it's not moving that much. And so you look at the computer and you say, oh, we just had some yield. And then you define that as mu equals 1. Then you reprogram the testing computer with the mu equals 1 value, and then you put in all of these other displacements. So the test is under displacement control. So you're telling the testing rig,
Actuator.
yeah, the term is actuator, but it's the machine that pushes and pulls the wall is a pretty advanced computer system, and you can tell it to control with displacement. And so it will, if this mu equals 1 is at 1 inch, then you say, okay, do 3 cycles at 1 inch. Then it increases to mu equals 1.5, so it would be 1.5 inches, and it does 3 cycles at 1.5 inches. Then it increases to 2, 3, 4, all the way up to 10. I think usually it fails before that. So you normally don't get all the way up to 10, but this is the testing protocol for any seismic testing of an FRP or FRCM strengthened
Correct.
number.
They actually are trying to add a new diagram for diaphragms and collectors now
Oh,
in
yeah.
AC 125 that's similar,
Yeah.
but
But so for fatigue loading, that would be like you have a bridge with like a truck going over it over and over again, and so it would be about the same load. And
a million times.
Yeah, and the load amount for fatigue is usually like the service load. So if you run a fatigue test, you're going to load a beam up to its service load, or maybe like 110% of the service load, like a million times. Fatigue tests can have millions of cycles in them, so that's the difference. But so for this,
That
yeah. So how did this beam ductility correlate to that other test? Is it just
what other test?
Sorry, not the other test, the graph that we were just looking at?
You have
Did
to-
you just chop it in half and only do one way?
Mhm. Have to move up.
Oh, because there's no FRP on top.
Right.
I think I didn't do anything. This is Miami,
Okay.
and one of the reasons we chose Miami to do it was because they've done it before. They've successfully had testing get approved, and so in my mind, I let them run with it. So I didn't really look too closely at the plan. So bad on me for not reviewing close enough, but NCR for Brad, for Uncle Brad. So yeah, they must have chopped it in half and gone down only. So they went down and then back up to 0 and then down again.
Uh-huh.
So yeah, but I don't know whether or not they're doing top and bottom this time with fully wrapped at the ends or going to do this again. But it was also approved by ICCES, the original test plan for this. So the reviewer missed it as well. But anyway, NCR on him as well. Should we pause a second?
Yeah.
If they have any questions or
That was one.
look at a lot of slides, yeah, we
Yeah, we
Talked
just
for
covered
quite
a
a
lot, so we're gonna stop talking for a minute. Let's you look at that.
Hỏi gì kìa?
So then just. Like that. And you just load it.
check the bottom half, I guess.
Either half, right?
Doesn't matter, yeah.
So
I don't know what they did,
Load it,
I think.
yeah. And so for confining the strip at both ends, is that from ACI chapter 13?
It came from hoping to keep it bonded long enough.
Yeah.
So I don't think we did any. Well, I'm not sure what they did. I mean, they may have looked at this. I think they were the ones that helped write it. Maybe not.
Does it say in seismic applications, the flexural FRP should be confined using FRP strips to completely wrap around the perimeter of the
Right.
section?
Yeah,
I was
so,
wondering if that's where that
But I'm
came
not
from.
sure. I don't even know if they give you guidance for how to design that. I think they might in another section. But anyway, yes.
Yeah, that's what they should be
I
doing.
mean, the stuff we're not telling these guys that we're jumping through hoops. Some of this testing has been done before on this that we're just trying to get more coding for them. Like, what really should be done and what should be done for this are not necessarily the same thing.
Right.
So, like, Francisco's was responding back to me from Miami saying, well, they usually have slabs above beams, so how would you fully wrap? I'm like, you don't worry about that, just do that. To get it through, because we've got anchors, we'll do that, we'll do whatever we need to do, but just give me the testing that passes, so we can get it in our code.
The ICC need to send anyone else to watch our tests, or we just send the tests to the ICC.
Say that again?
Does the ICC need to send someone to watch?
No, so once a lab is accredited for testing, so ICC will go and witness to make sure they are doing things properly. And there's also another company called International Accreditation Service that accredits labs to make sure they're doing things. So both ICCES and IAS will go to a lab, make sure they can do it properly. Like if they show them you do the test, show them how you collect the data, and then once you're approved for the testing, they don't need to go witness anymore.
So they just need to watch like one test.
Yeah.
Oh, that's what I want to say. If we fail, we cannot do it again.
No, we do as many times as we want.
But we have to do like another, like, if we fail at this time, we need to do it another time.
Yeah, maybe,
It's more expensive too.
right.
Yes, so they inspect the lab where the testing is done. So they've inspected the Simpson lab to make sure we do things right. And they've inspected the lab at University of Miami that did this testing. And they inspected the lab at NC State University that did the other testing. Also, something they had to do was inspect our production facilities, right? They come
Yes.
to where we make the FRP and they watch it being made and make sure that we're producing it the right way.
Yeah, I think every quarter,
4 times a year.
maybe twice a year only. I don't remember off the top of my head, but ICCES has to do that. UL has to do that because of our fire testing. NSF has to do that because of our drinking water testing. So there's 3 agencies just for our products alone that have to go and inspect, and we have to pay for it every single time. So
I see.
cost of doing business. So we're running up on an hour, and we're only about halfway through. Do we want to find a good stopping point, like after this section, or what do you think?
Yeah, I mean, we
We
can.
start these, I think we have Friday, Monday, and Tuesday, do nothing. So, yeah, no meeting
Right, that's right.
next
So
Tuesday.
Tuesday we should,
Go longer?
You can finish this on this week. Okay.
Well, we'll see. I don't know if we want to go that long. If that took an hour,
Yeah, well, we can just
We'll see.
kind of keep going and see.
we've got a lot of stuff to do for Naveen, to help Naveen today.
Yeah.
So in-plane shear strengthening of slabs is a little bit weird. We didn't actually do any tests for this because there's nothing in the acceptance criteria now that has that tells you how to do this test. So basically, that highlighted language is what we added to our code report. And my argument to ICCES was Fife has that language in their code report, and you don't tell us how to do that testing in the AC. So how did they get it in their code report? And if they can have it in theirs, I want it in mine. And so that was the argument that helped it get in our code report, and we didn't have to do any testing. It's not necessarily the appropriate way to do it, but I said if I can't have it in mine, then you need to take it out of Fife's code report. So apparently they didn't want to do that. So that I mentioned a little while ago, they are currently adding diaphragm testing and collector testing to the acceptance criteria right now, and so soon we'll be able to do testing to show that we can do that as well.
But so I guess the idea of the in-plane shear strength of a slab, that we're increasing it, is based off the fact that we have wall testing. So we tested a wall in all these different ways in plane shear strengthening. And so the idea is if it's a diaphragm, it's going to be kind of the same. I think that's how we are able to have that in our code report now. But they might add more requirements for testing of diaphragms, and so we might have to do more testing.
Right, correct. We will be doing testing at some point. So I showed these pictures already before, but in-plane shear strengthening of concrete walls, this was done, Miami oversaw the testing, but it was done at a university in the country of Colombia in South America. And hopefully soon we'll have anchored specimens as well. So these results were only 13 to 35% increase in strength, but got us the ability to add this into our code report. So this is kind of going backwards, but in our original FRP code report, this is the testing. When I say previous testing, this is the testing we had So again, the same rig at NC State, where they squish the columns vertically, and we could get quite a big increase in load, whether it's 1 layer of glass or 2 layers of glass fabric. And the units were all metric for those guys in Europe.
Right.
Yes.
What is 915G?
What is the?
915G, what is?
The 915 gram.
That's basically our 27-ounce glass fabric. That's grams per square meter, I think. Yeah.
So Brad made a presentation to present information to people at S&P Clever in Europe. And so all the units are in metric because he was presenting it to European engineers that are used to seeing things in metric.
Because if I said 27-ounce, they're like, what's that in grams? So just like you did, or Ling did just now.
Yeah.
What does that mean? So this, I believe, was 370, I think is our 22-ounce carbon fabric. But we have control 1 layer and 2 layer. And the one on the right, you see that column basically blew up. It was so strong that once it finally broke, the fabric broke, the column just exploded. So from what I hear, pretty exciting testing. We did beams and flexure with FRP at 10% to 55% increase, it looks like. Beams and shear, we had over 200% increase in all the specimens, so it's pretty big. Oh, sorry, this is a little different ratio. These ratios are the ratio of the calculated ultimate to the actual ultimate failure load in our test. So a little bit different than the ratios I showed before.
But it can lead from the unstrengthened member or strengthened?
No, calculated from the AC 125 design equations. So basically take out phi factors, or make phi factor 1, take out the xi factor, any other reductions, and calculate an ultimate capacity based on those equations. And the only thing you need to do to pass the test is actually get an ultimate failure load higher than that calculated failure load. Right.
And this is interesting so like for none control, this is a beam, this is just a reinforced concrete beam. And if you use ACI 318 to calculate the capacity, what?
No, just go ahead.
He's beating you to the punch.
Cooking.
If you calculate the capacity using ACI 318, you'll get a capacity of 17.2 kips, but the actual failure load is 48.5 kips. So this kind of shows how conservative the shear design equations are, because it's very important that you don't have a shear failure and instead you have a flexural failure. So in addition to the phi factors that we use and the seismic design detailing we use to prevent shear failures, the equations themselves are very conservative. I think for flexure, you wouldn't have a ratio like this of 2.8.
Well, if you go back a slide or two, it'll show you. Yeah. So those aren't the increases I talked about in the last slide. Those are the same thing I just said. So those are calculated ultimate to test.
Yeah.
The other way around. Test to calc, yeah.
So between
10 and 55.
Yeah. You're being much more conservative in the design with shear than you are in flexure.
And this is a picture of one of the shear failures. So a diagonal crack that basically right through the entire element. Not really debonding because it's a chunk, that's a big old chunk of concrete coming out there. So out of plane flexure on walls with FRP. So just like the testing we did with FRCM, and this is the actuator that pushed and pulled. And there's a frame just like this. Actually, no, there's not. There's just a horizontal member on the back side of the wall that helps pull the wall back towards And so this shows a failure of a debonding strip that was bonded really well because it pulled chunks out of the CMU wall. I don't think I have loads on that one. In-plane shear, again the stair step crack, we saw that on FRCM earlier. So this is our wall slab connection, or the L-shaped shear transfer connection we talk about with our 45 glass. And this works out to, I think, about ultimate load of 11 kips per foot.
8.75. Right,
Well,
for the smaller.
I think the ultimate was 11, I think. Or no, I think you're right, Maybe the higher one was 11, but
Yeah, the higher one was one.
yeah.
But the minimum we use 8.75.
So this shows the test setup. There's a 1 foot strip of slab between these walls. These walls were anchored down to the strong floor. And then we put this L-shaped FRP between the wall and the slab, and then pushed and pulled on that until it broke.
We want to break for it.
Yes,
Or get into the next confusing bracket.
and while they talk to each other, and take a potty break.
Yeah. Do you just want to break for a second after talking about the?
All that testing.
Yeah. So this is basically all the testing that went into our first FRP code report. So we added all this stuff recently to get the seismic testing because we had to add it. But this testing was all done in like 2013, 2014, when we were just starting getting into FRP. This testing was done a while ago. And we watched a video of this test in a previous training session. But anyway, I don't know if you have any questions about any of this.
Nói gì?
So is the team hold up like the facilities and just design tests? That'd be much.
But there is-
like
Yeah, we will
report testing for like all
Yeah, we support the
manufacturers. So because they
Well, it's
don't
all
like to
happening.
do it right, we
Yeah, let's
kind
have
of
it
expect
easier.
them to like help us out with some of the design
Right,
and
and set up,
experiments and
right.
stuff, and like we need to like approve it, but we need to be like, hey, you guys have done this before, what's the best way
Right,
to do
right,
it?
you don't wanna like necessarily tell them how to do the test.
Right.
Like, and then it'd be like a.
Mày bóng rồi.
We don't wanna
Not
reinvent the
consider
wheel.
everything, right?
Yeah, it'd be like, it's a good idea for this code test, and it's like the most important thing for this testing is
It'd
getting,
be
Một
like,
cái nào
getting
right,
code.
làm nhớ mọi người.
right, right.
Cái đó một.
Then it's like strong enough to withstand.
Whereas like.
But like for NC right?
It's what?
Just feel like the state like licensed. and
Cái
stuff.
dễ dàng đâu bao giờ.
I think we agreed that NC State has done
Oh, okay.
that code testing.
So it is gonna hold up, like an accredited lab.
If they, I mean, if they really know what they're doing, so like NC State, like, put out a ton of code testing. So if we like went to Berkeley, then I'm sure they have instructors like they've never done
Đó là
this
tác
before,
tác công việc.
then we would need to be much more actively involved in that figuring out the right way to test everything.
Tiếp fit. Tiếp fit.
Yeah. Again, it depends on who has more experience.
Hỏi đúng rồi. Thứ ba là
Ready?
Oh.
How do I get out of escape? It's weird that it locked me in.
So what we test, we did for stiff.
Stiff
I test for that.
Basically tensile testing. So where you make a witness panel, you cut little coupons out,
So why?
and then you pull it.
So why another committee didn't do that? I think that's why.
Well, so we were, well,
So it's not really something that's in, I mean, it is in the code report, but every manufacturer has a stiffness in their code report. And every other manufacturer's stiffness in their code report is lower than ours.
Oh, or the way you take it.
So you have to compare all of them together. But Fresnay's is higher, right? What are they?
They have one fabric, I think it's 9 or 10 ounce carbon, that's higher than our carbon fabric. But we never see them, we never compete against them very much.
Fresnay.
Oh, it's not on there.
There's a
I think this is an old, actually, slide. Wait,
How do you, well, I'm really guessing that's still that.
Cái này là test được nữa.
Are you gonna add it with an AY, and with an AY?
Thực ra cái khúc này như do là mình lớn hơn mình biết vào
SS.
tức là hai cái test mình lớn
Vâng.
hơn.
ZZ.
Anti-face, okay, cứng nhất là anh nghĩ là những cái này là test.
Oui.
But so they're a decent sized competitor for S&P,
Okay.
and it's a French company, but they don't really compete much.
Cái hồi đó được có nghĩa là cái sản phẩm của mình có độ cứng lớn nhất trong cái hãng
The twins used to work for them.
Right.
tiếp phệt và cứng nhất.
Chứ không phải là do mình có mà đã không có, mà là do mình lớn nhất.
Tiếp phệt chứ không phải tiếp phệt.
Got it.
Yeah.
So, this slide we put together for our salespeople to show that we had the most complete code report compared to their competitors. I actually did update this, and I don't. Maybe Fresnay does. No, maybe they let their code report lapse. Maybe that's why it's not on here anymore. I don't remember.
Okay.
Um,
Yeah, but so they do have a fabric that's stiffer, but it's they don't really compete like Structural and Fife and Sika do. And also, it's worth noting we have fabric. Our stiffness is 14,200, and Structural Technologies now has a fabric that's 14,000 KSI. So it's very close, like 1%, 2% different. So, you know, I think it would be easier to substitute their fabric for ours than it would be like Fife's, because Fife's is like 20% different or
Mhm.
something.
Yep. So I just included this slide to show we did some environmental testing where we basically, you take panels of our FRP, soak them in different liquids for a certain amount of time, and then you take them out and tensile test them, and you have to retain a certain amount of the tensile strength. And so the values that we show in our data sheets for all of our code listed products or products in our code report are some of them are reduced because of this testing. So some of them are lower than they would have been if we didn't have to do durability testing.
So you create, say you create 2 panels of FRP, and one of them you test as a control. So it's just, you make the FRP panel and then you do a tension test on it. It's a control specimen. Then you have experimental specimens, like your test specimens. And for the test specimens, you expose them to these different things. So one of them is just regular water. Another one is water with salt in it. Alkali resistance is, there's chemicals in the water, calcium carbonate or something like that. Some kind of
Sounds
chemical
good.
that
Yeah.
attacks the FRP. And then there's no liquid, they just expose it to high heat, 140 degrees Fahrenheit, maybe 60 degrees Celsius, I don't know.
I don't either.
So anyway, so they take the test panels and expose them to all these things, and then they do the same tensile test on that. And so when they do the tensile test on the FRP that's been exposed to all these things, the value of that tensile test has to be equal to 90% of the control panel that has not had any of these things exposed to it. And so after you expose it for 1,000 hours, it has to have 90%. After 3,000 hours, it has to have 85%.
Did you do like 10,000 hours? Like more than 1 year?
Yeah.
Yeah, 14 months.
1,000 years.
Is there not a percentage for 10,000?
No, they don't. They don't actually require tensile testing after 10,000 hours. You just look at it.
Seems okay.
Yeah.
Except for Caltrans.
Oh, right.
They do require a 14.
Yeah.
A 14-month tensile test.
Yep.
So then,
ICC
doing
doesn't,
it?
but Caltrans.
then we do it to be
We
intelligent.
did it. Yeah, we had to redo the testing and start over for them.
So it took another year.
Yeah.
Another
Yeah.
416 days.
No shortcut for that. Alright.
Leave it to Caltrans. This is another chart. Oh, actually, this is from AC 434. The same durability testing, and similar things that we talked about for tensile retention from the testing. I don't know if we need to go into detail really here. More durability testing. I mentioned NSF before, so that's, is it National Science Foundation? Is that what NSF stands for?
Yeah.
Basically, they have drinking water. NSF 61 is drinking water approval. So yeah, if you put your elements in a water solution over a certain amount of time, are there bad chemicals that leach out into the water that you couldn't drink it anymore? So no beer 30. Not really anything I need to say about that, I don't think.
Yeah, it's like if we're doing strengthening of something that's exposed to drinking water, then that's why this test
Or it's like-
is important.
And important if you ever did like inside of pipes, or like,
Right.
if you're doing it inside of a tank, like if it's holding
Yep.
water, or
Yep.
it's anything like that, so it's actually, I mean, makes you be
Right.
able to use it in a lot more applications.
Or
Care
in
about that,
a lake or ocean,
right?
if you could drink the water, then hopefully fish can swim in the water.
Wastewater treatment plants, bunch of stuff like that, it's really important.
Maybe not wastewater because nobody's drinking that.
Well,
But
they're treated.
that's true.
On
Good
the other
point.
side.
On the other side, once
Yeah,
it's
yeah,
done.
that's true. UL listing. So this is our full-scale fire testing. We have a UL listed assembly there for 4 hours for both of our FRP and FRCM materials. And there's our FRCM. Okay, I'm not sure what I was going to say about. Oh, I think on Chief's list was show our competitors' data sheets, maybe. I don't know. So a little bit different than the way we show things, and I've actually been thinking about adding. Actually, do they? I don't even show it here. But some of our competitors show basically the minimum stiffness per inch on their data sheet, and that's something that we hadn't or don't show now that I've been considering adding, because a lot of our competitors are showing that now on their data sheet. But if you know our values, like Griff has mentioned before, our modulus is 14.2 and theirs is 11.9. Their tensile strength is 121,000 psi. What's ours off the top of your head?
Ours is 128.
So not much higher, but this value doesn't come up very often when designs anyway. But here actually they have tensile strength per inch of width here. They don't have the modulus or stiffness per inch, but and this is all taken from Fife's SCH41, so the equivalent of our 22-ounce carbon fabric.
And one thing that's kind of weird that Fife does that we and some of our other competitors do that we don't think is necessary is provide this column. It says typical test value. Other than just if someone is interested in what this is, there's no reason to have this. The important thing is the design value, which is the typical test value that's been reduced for design. So the number that you use in a spreadsheet or to find the strength of the material is always going to be this column. So if you look at Simpson's data sheet, we only include our design values. We don't include the typical test values.
Is it just to make them look stronger? I mean, like what?
Maybe
Or
it-
like is it anyone
I think it's
using that
before-
value to design?
I think it's before durability testing. So I don't know. I mean, Fife does questionable things with their designs, so they may talk engineers into using higher strength sometimes, just
Oh, is it?
because
Right,
they
using
feel like
as,
it. Yeah,
yeah, using it as like a,
I don't know.
do they stamp their drawings, right?
No.
So then,
They pay somebody to do it for them. Yeah.
I'm just wondering if they're accepting liability if they're telling somebody to use it.
I think they farm it all out.
There are states or areas in the U.S. that don't require code reports, and so if you don't require a code report, you don't have to do durability testing, and maybe that's when they use their higher values. I don't know, but
Yeah, just curious.
yeah. I think it's all there, I guess.
It's a good distinction.
And so we, I think most of you have all seen product equivalency at this point, but basically we compare our fabrics to Fife. Well, this particular one is our 22-ounce fabric to Fife's similar fabric. It shows that we're stiffer, and then we add the product equivalency note there.
Yeah, so we didn't talk about this template in our design, presentations. Because we're not really designing anything with this template. We're just showing if somebody specifies another product, we compare our product to it, and we provide a DCR where the demand is the competitor's product and the capacity is our product. And what we use for the DCR is the E times A, the stiffness times the thickness of the material, because that's the best way to compare the strength of two different carbon fabrics, or any fabric.
Yeah, the limit DCR should be 1.0.
Oh yeah, we changed that, right, from
Yeah.
product
It's an
equivalency.
old image maybe.
Good catch.
I know. Nice one. NCR and Brad for making a bad presentation.
Yeah.
So that should be 1.0.
Thank you. Okay, that's it. We actually got through that fairly quickly.
Please.
Any questions you guys can think of? Or everything's super clear? Okay,
Thank you.
thank you.
Yeah.
Thank you.
Thanks, Brad.
Sure.